Welcome to this in-depth lecture on van der Waals and Casimir stiction and adhesion in micro and nano electromechanical systems. These are two of the most critical failure mechanisms in miniaturized devices, and understanding their differences is essential for device design. As we shrink mechanical devices down to micro and nanometer scales, something remarkable and problematic happens. Surface forces that are completely negligible at the macro scale become dominant. This leads to a phenomenon called stiction, where surfaces stick together permanently. Let me pose a question. Why does stiction matter so much at small scales? The answer lies in the scaling laws. As we shrink a device by a factor of 10, the volume decreases by 1,000, but the surface area only decreases by 100. This means surface-to-volume ratio increases by a factor of 10. Let's write this mathematically. If lambda is our scale factor, then volume scales as lambda cubed, while area scales as lambda squared. So the surface-to-volume ratio scales as lambda to the -1. This means at smaller scales, surface effects dominate over bulk effects. For example, if we shrink a device by a factor of 1,000, surface effects become 1,000 times more important relative to volume effects. This is why stiction becomes such a critical issue in MEMS and NEMS. Before we dive deeper, let's clarify what MEMS and NEMS are. MEMS stands for micro-electromechanical systems, with dimensions typically in the micrometer range, from 1 to 1,000 micrometers. MEMS devices include accelerometers in your smartphone, pressure sensors in car tires, and digital micromirror devices in projectors. NEMS stands for nano-electromechanical systems, with dimensions from 1 to 1,000 nanometers. These include nanoresonators, molecular sensors, and quantum mechanical devices. Now let's discuss van der Waals forces. These are weak, intermolecular forces that arise from quantum mechanical fluctuations in electron distributions. There are three types: Keeson forces between permanent dipoles, Debye forces between permanent and induced dipoles, and London dispersion forces between instantaneous dipoles. Imagine two molecules approaching each other. Even if they're electrically neutral overall, there are instantaneous fluctuations in their electron clouds. When one molecule's electrons happen to be on one side, this creates an instantaneous dipole that induces a dipole in the neighboring molecule, leading to attraction. The potential energy for van der Waals interactions between two molecules follows an inverse sixth power law with distance. U van der Waals equals -c over r to the sixth power, where c is a constant that depends on the molecular polarizability, and r is the separation distance. But what about macroscopic surfaces and MEMS devices? We need to sum up all the pairwise interactions between atoms in two surfaces. This was first done by Hamaker in the 1930s. Hamaker integrated the pairwise interactions, assuming continuous media. For two flat parallel surfaces separated by distance d, the van der Waals energy per unit area is given by the following expression. E van der Waals equals -a Hamaker over 12 pi d squared, where a Hamaker is the Hamaker constant, typically on the order of 10 to the -19 joules for most materials. The force per unit area, which is the pressure, is the derivative of energy with respect to distance. P van der Waals equals -a Hamaker over 6 pi d cubed. Notice this goes as 1 over d cubed for surfaces, compared to 1 over r to the sixth for molecules. Let's do a numerical example. Consider two silicon surfaces separated by 10 nanometers. The Hamaker constant for silicon is approximately 10 to the -19 joules. What is the van der Waals pressure? A Hamaker equals 1 times 10 to the -19 joules, and d equals 10 nanometers, which is 10 times 10 to the -9th meters. P van der Waals equals 1 times 10 to the -19 over 6 pi times 10 to the -8 cubed. This gives us approximately 53,000 pascals, or about half an atmosphere of pressure. That's substantial. Now here's the key point. If we decrease the separation to 1 nanometer, the pressure increases by a factor of 1,000 to 53 megapascals. This is enormous. It's like having 5,000 atmospheres of pressure trying to stick your surfaces together. Now let's turn to Casimir forces. These are even more exotic. They arise from quantum fluctuations in the electromagnetic vacuum. Even in perfect vacuum, quantum field theory tells us there are virtual photons constantly popping in and out of existence. In 1948, Dutch physicist Hendrik Casimir made a remarkable prediction. He said that if you place two uncharged, perfectly conducting plates very close together in vacuum, they will experience an attractive force. Why do uncharged plates in vacuum attract each other? The answer lies in the boundary conditions. Between the plates, only certain electromagnetic modes can exist, those whose wavelengths fit an integer number of times in the gap. Between the plates, only certain wavelengths fit, like standing waves on a string. Outside the plates, all wavelengths are allowed. This means there are more vacuum fluctuation modes outside pushing the plates together than inside pushing them apart. The Casimir energy per unit area between perfectly conducting plates is negative pi squared h bar c over 720d cubed, where h bar is Planck's constant divided by 2 pi, and c is the speed of light. The pressure is the derivative, negative pi squared h bar c over 240d to the fourth. Notice this goes as 1 over d to the fourth, which is a steeper dependence than van der Waals. This brings us to a critical difference between van der Waals and Casimir forces. Van der Waals pressure scales as 1 over d cubed, while Casimir pressure scales as 1 over d to the fourth. This means that at large separations, van der Waals forces dominate, but at very small separations, Casimir forces can become comparable or even dominant. At what separation do they become comparable? We need to set the two pressures equal and solve for d. This gives us a crossover distance. Setting a Hamaker over 6 pi d cubed equal to pi squared h bar c over 240d to the fourth and solving for d. The crossover distance is pi cubed h bar c over 40 a Hamaker. Plugging in typical values, this is around 10 to 20 nanometers. So below 10 to 20 nanometers, Casimir effects dominate. Above this, van der Waals effects dominate. This is crucial for understanding stiction in different device regimes. Let's calculate the Casimir pressure at a separation of 10 nanometers. We'll use h bar equals 1.05 times 10 to the negative 34 joule seconds, and c equals 3 times 10 to the 8th meters per second. P Casimir equals pi squared times 1.05 times 10 to the negative 34 times 3 times 10 to the 8th, all over 240 times 10 to the negative 8 to the fourth. This gives approximately 130 pascals at 10 nanometers. This is smaller than the van der Waals pressure at this separation, confirming that van der Waals dominates at this scale. But at 1 nanometer separation, the Casimir pressure increases to about 1.3 megapascals, becoming much more significant. Now let's discuss the fundamental physical origin of these forces, because this is where they truly differ. Van der Waals forces are ultimately electromagnetic in origin, arising from correlated fluctuations in charge distributions within matter. Van der Waals forces come from matter fluctuations that are mediated by virtual photons. They depend on the material properties like polarizability and dielectric constant. Casimir forces, on the other hand, come from vacuum fluctuations themselves. They're a boundary condition effect on the quantum vacuum. In principle, they exist even for materials with zero polarizability, though in practice, material properties do modify them. There's another important difference we haven't discussed yet: retardation effects. Van der Waals forces are modified at larger separations by the finite speed of light. This is called the retarded regime or Casimir-Polder regime. For van der Waals forces, retardation effects become important when the separation d exceeds the characteristic wavelength lambda c, which is roughly 100 nanometers. In the retarded regime, van der Waals pressure changes to 1 over d to the fourth, the same as Casimir. This is because retarded van der Waals forces and Casimir forces are really the same thing. They're both manifestations of quantum electrodynamics. Now let's talk about the practical implications for device design. In MEMS, typical gaps are hundreds of nanometers to micrometers. Here, van der Waals forces dominate, and retardation effects are important. Consider a MEMS cantilever beam with a 500 nanometer gap to the substrate. Let's calculate if van der Waals stiction will occur. We need to compare the van der Waals pressure to the restoring force from beam bending. The beam experiences a downward van der Waals pressure, trying to pull it to the substrate, and an upward elastic restoring force from bending. Stiction occurs when van der Waals force exceeds the maximum restoring force. The elastic restoring force is K delta, where K is the spring constant, equal to 3EI over L cubed. E is Young's modulus, I is the moment of inertia, L is the beam length, and delta is the deflection. For silicon, Young's modulus is 170 gigapascals. Let's say the beam is 100 micrometers long, 10 micrometers wide, and 2 micrometers thick. The moment of inertia is Wt cubed over 12, which equals 10 micrometers times 2 micrometers cubed over 12. Plugging in the numbers, K equals 3 times 170 times 10 to the 9th times 6.67 times 10 to the negative 24, all over 10 to the negative 4 cubed. This gives a spring constant of about 0.34 newtons per meter. This is very soft. These beams are very compliant. There's a critical concept called pull-in instability. As the beam deflects toward the substrate, the van der Waals force increases faster than the restoring force. Beyond a critical separation, the beam snaps down irreversibly. The critical separation is approximately 2/3 of the initial gap. For our 500 nanometer gap, pull-in occurs when the gap decreases to about 330 nanometers. Once the gap falls below the critical value, stiction becomes inevitable. The beam will stick to the substrate and cannot be released by the elastic restoring force alone. In NEMS devices, gaps are often just a few nanometers. Here, both van der Waals and Casimir forces are significant, and surface roughness becomes critically important. Surface roughness for well-prepared surfaces is typically 0.5 to 2 nanometers root mean square. This means the actual contact area is much smaller than the nominal area, and the effective gap is larger than the ideal gap. Real surfaces are rough. The actual separation is determined by the highest disparities on each surface. This increases the effective gap and reduces stiction forces, which is actually beneficial. Now let's discuss temperature effects. Both van der Waals and Casimir forces can have temperature dependence, but in different ways. Van der Waals forces have weak temperature dependence through the Keesom orientation contribution. The Keesom contribution goes as 1 over kBt, where kb is Boltzmann's constant and T is temperature. But for most materials, London dispersion forces dominate and are temperature independent. Casimir forces, on the other hand, can show temperature dependence at large separations, above about 1 micrometer. At these distances, thermal photons contribute to the vacuum fluctuations. The thermal wavelength is h bar c over kBt. At room temperature, this is about 7.6 micrometers. When the gap is comparable to this, thermal corrections become important. For typical MEMS and NEMS gaps, which are much smaller than the thermal wavelength, temperature dependence is usually negligible. Let's discuss how material properties affect these forces. Van der Waals forces depend strongly on material through the Hamaker constant, which is related to the dielectric properties. For static properties, the Hamaker constant is approximately 3/4 kBt times the difference of dielectric constants squared over their sum squared, but more accurately, it depends on the full frequency-dependent dielectric function. Typical Hamaker constants range from 0.4 to 4 times 10 to the negative 19 joules. Water has a low value around 0.4, while metals like gold have high values around 4. Casimir forces are modified by finite conductivity of real materials. The ideal calculation assumes perfect conductors, but real metals have finite conductivity, especially at low frequencies. The real Casimir pressure is the ideal pressure times a correction factor eta that depends on conductivity sigma and separation d. For good conductors at small separations, eta is close to 1. How do we actually measure these tiny forces? Several experimental techniques have been developed. The most famous is the atomic force microscope, or AFM, which uses a cantilever beam with a sharp tip. The AFM brings the tip close to a surface while measuring the deflection of the cantilever. From the deflection, you can calculate the force. By doing this at different distances, you build up a force versus distance curve. Van der Waals forces were confirmed experimentally in the 1950s and 60s using surface force apparatus measurements. The distance dependence matched the theory beautifully. The Casimir effect was first measured by Sparnay in 1958, though with large uncertainties. More precise measurements came in the 1990s and 2000s using micro-mechanical oscillators and AFM. Lamoureux in 1997 achieved 5% agreement with Casimir's theory using a torsion pendulum. Modern measurements have pushed precision below 1%. Now let's discuss practical design strategies to avoid stiction failure in MEMS and NEMS. This is crucial for reliability. There are several approaches. Strategy 1. Increase the stiffness of movable structures. Make beams thicker or shorter to increase their spring constant. This increases the restoring force that opposes stiction. The trade-off is that stiffer beams require more actuation force to move them, which can increase power consumption or require higher voltages. Strategy 2. Reduce the contact area by adding dimples or bumps to surfaces. This reduces the total van der Waals or Casimir force by limiting the area over which surfaces can come into close contact. Dimples are small protrusions on the surface. When the surfaces come together, only the dimples make contact, creating a much smaller effective contact area. This can reduce stiction force by orders of magnitude. Strategy 3. Use surface coatings to modify surface energy. Self-assembled monolayers or hydrophobic coatings can reduce adhesion. The most common is coating with fluorinated molecules. Hydrophobic coatings like perfluorodikyltrichlorosilane can reduce the effective Hamaker constant by inserting a low-energy interface layer. This can reduce van der Waals forces by a factor of 2 to 5. Strategy 4. Use mechanical stoppers to prevent surfaces from ever coming into very close contact. This keeps the gap above the critical distance where stiction becomes irreversible. Strategy 5. Implement active release mechanisms. Some devices include heating elements that expand structures to break stiction or use ultrasonic vibrations to provide energy to overcome adhesion. Let's look at a concrete example, an RF-MEMS switch. This is a cantilever beam that moves down to make electrical contact with a transmission line. The beam must make good contact when down, but release reliably when the voltage is removed. The switch beam has dimples to reduce contact area. When a voltage is applied, electrostatic force pulls the beam down. When voltage is removed, the beam must spring back up, overcoming van der Waals adhesion. Typical RF-MEMS switches must survive 1 billion switching cycles without stiction failure. This is extremely demanding. Careful design of all parameters is essential. Let me give you a biological analogy that beautifully illustrates these principles. Gecko feet use van der Waals forces to stick to walls and ceilings. Each foot has millions of microscopic hairs called setae, and each seta has hundreds of even smaller branches called spatulae. The spatulae are only a few hundred nanometers in size. When they come into close contact with the surface, van der Waals forces provide adhesion, but the gecko can control the angle of contact to easily detach. The total adhesive force is enormous. A gecko can support 130 kilograms with a single toe, yet it can detach effortlessly by peeling its toes at the right angle, which reduces the contact area progressively. The key principles are hierarchical structures to maximize surface area and controlled contact geometry to enable easy release. Engineers are now mimicking this in synthetic adhesives for MEMS grippers. As we push into the deep nanoscale, even more exotic quantum effects become relevant. There are proposals to use modified Casimir forces for actuation in NEMS or to measure Casimir torques between anisotropic materials. Casimir torques arise between birefringent crystals with different optical axis orientations. These torques could potentially be used for ultra-low friction nanoscale bearings or for angular actuation without electrical contacts. In certain geometries and material combinations, Casimir forces can even be repulsive. This requires careful engineering of the dielectric functions, but has been demonstrated experimentally. Repulsive Casimir forces could solve the stiction problem entirely. There's also the dynamic Casimir effect, where moving boundaries can create real photons from vacuum fluctuations. This has been observed in superconducting circuits and might have applications in quantum information processing. For ultra-sensitive NEMS sensors, like nanomechanical mass sensors or force sensors, thermal and quantum noise set fundamental limits. At room temperature, thermal noise dominates, but at millikelvin temperatures, quantum zero-point motion becomes the limit. The mean square thermal displacement is kBT over K. For very soft nanoresonators at room temperature, this can be several nanometers. The quantum zero-point fluctuation is h bar over 2 meters omega, where m is the effective mass and omega is the resonance frequency. At low temperatures, this becomes the limiting noise floor. Interestingly, both van der Waals and Casimir forces contribute to thermomechanical noise through fluctuation-dissipation relations. The fluctuating forces from vacuum and thermal photons cause random motion of the NEMS structures. Let me summarize the key points from this lecture. First, van der Waals forces arise from correlated charge fluctuations in matter, while Casimir forces arise from boundary effects on vacuum fluctuations. Van der Waals pressure scales as 1 over d cubed for surfaces in the non-retarded regime and transitions to 1 over d to the fourth in the retarded regime beyond about 100 nanometers. Casimir pressure scales as 1 over d to the fourth. It dominates at separations below 10 to 20 nanometers. Both forces cause stiction failures in MEMS and NEMS, but van der Waals is more important for MEMS at typical gaps of hundreds of nanometers, while Casimir becomes relevant in NEMS at few nanometer gaps. Design strategies to mitigate stiction include increasing stiffness, using surface coatings to reduce adhesion, adding dimples to reduce contact area, and implementing active release mechanisms. Surface roughness, usually seen as a nuisance, actually helps reduce stiction by increasing the effective separation and reducing contact area. Material choice matters significantly. Hemiger constants vary by an order of magnitude between different materials, and coatings can modify surface energy. Temperature effects on the forces themselves are usually small for typical MEMS and NEMS gaps, though temperature affects other aspects like thermal expansion and material properties. Let me close with some open questions and future directions. Can we harness Casimir forces for useful work in NEMS devices? Can we achieve true repulsive Casimir forces in practical geometries? Can we reach the quantum ground state in mechanical resonators, where quantum effects dominate? This would enable quantum sensing and fundamental tests of quantum mechanics at mesoscopic scales. How do these forces behave in complex environments like liquids or ionic solutions? This is important for bio, MEMS, and lab-on-chip applications. Can we engineer the geometry and materials to create custom force landscapes? This could enable new types of self-assembly or reconfigurable nanodevices. Understanding van der Waals and Casimir forces is absolutely crucial for designing reliable MEMS and NEMS devices. As we continue to push to smaller scales, these quantum mechanical effects will only become more important and more interesting.